Our galaxy is just one of trillions, each one a vault of cosmic secrets. We are about to journey through 50 mind-bending facts that will fundamentally change how you see the night sky. By the end, you will understand the true nature of our universe, from cosmic cannibals and invisible matter to universe-shaping collisions. What is the dark force that holds galaxies together, and how do galaxies devour each other to grow? When you look up at the stars tonight, what will you truly be seeing? Galaxies are not the solitary islands they appear to be in the deep night sky. They are profoundly social, existing in vast communities held together by gravity. Our own home, the Milky Way, is part of a neighborhood known as the local group. This family of galaxies includes the majestic Andromeda, a spiral galaxy even larger than our own, and more than 50 other smaller galaxies, all caught in an endless, graceful dance around one another. But this is just the beginning. The local group itself is a single district within a much larger metropolis, a supercluster of galaxies. Think of the universe not as a random scattering of stars, but as a magnificent cosmic web. Enormous filaments of galaxies stretch across the cosmos, intersecting at dense clusters, all separated by unimaginably vast, dark voids of almost nothing. Our entire local group is just one thread in this immense, glittering tapestry. Yet for all their brilliant communities, galaxies are masters of disguise. The glittering stars and glowing gas clouds we see are merely the visible tip of a cosmic iceberg. The vast majority of a galaxy, a staggering 85% of its total mass, is made of something we cannot see, touch, or directly detect. This mysterious substance is known as dark matter. We know it exists only because of its powerful gravitational pull. Stars on the outer edges of spiral galaxies orbit at such incredible speeds that, according to the laws of physics, they should be flung off into the emptiness between galaxies. The only thing holding them in place is the immense gravitational grip of an unseen mass, a hidden scaffold of dark matter that envelops the entire galaxy. This ghostly matter does not emit, absorb, or reflect any light, rendering it completely invisible to our telescopes. So when you gaze at a photograph of a majestic spiral galaxy, you are not seeing its true form. You are looking at a luminous pattern painted onto an invisible, massive, and deeply mysterious skeleton. This invisible framework of dark matter does more than just hold galaxies together. It sets the stage for cosmic events of unimaginable scale. The serene galaxies we see are not frozen in time. They are in constant, slow motion, often on a direct collision course with their neighbors. The very idea of galaxies colliding sounds like a recipe for total destruction, a cosmic car crash of epic proportions. Yet these mergers are not only common, they are one of the universe's primary engines of creation and change. Our own Milky Way is living proof of this, having consumed smaller galaxies in its past and bearing the scars and streams of stars from those ancient encounters. And our future holds an even greater spectacle. In about 4.5 billion years, the Milky Way and the Andromeda Galaxy, the two largest members of our local group, are destined to meet. They are currently racing toward each other at a staggering speed of nearly 250,000 miles per hour. But when these two titans finally meet, a direct hit is almost impossible. The spaces between stars are so vast that the stars themselves will simply pass by one another, like two swarms of bees merging into one. The real drama unfolds in the gravitational chaos. The delicate spiral structures of both galaxies will be torn apart, their shapes stretched and twisted beyond recognition over billions of years. As immense clouds of gas and dust are violently compressed, they will ignite a firestorm of new star birth, a brilliant stellar baby boom that will light up the newborn galaxy. This merged entity, a colossal elliptical galaxy that some astronomers have nicknamed Andromeda, will be the new home for our solar system, flung into a new orbit but likely surviving the tumult. Galactic collisions are not an end, they are a violent, beautiful, and fundamentally creative rebirth. This grand cosmic web, woven from dark matter and reshaped by collisions, is almost unimaginably vast. While our local neighborhood contains dozens of galaxies, the observable universe, the part we can possibly see, holds an estimated 2 trillion of them. To even begin to grasp that number, think of every single grain of sand on every beach and in every desert on our entire planet. The total number of galaxies in the known universe is roughly equal to all those grains. Each one of those galaxies is an island universe in its own right, home to hundreds of billions of stars and likely trillions of worlds. This staggering scale means that for every star you can see on a clear night, there are countless entire galaxies, each filled with their own billions of suns hidden in the darkness beyond. And this realization leads to a profound and humbling truth. The vast majority of this cosmic ocean, filled with its 2 trillion galactic islands, is forever beyond our reach. The expansion of the universe is carrying them away from us so fast that their light will never reach us, placing them in a realm of permanent isolation. We are surrounded by an infinite cosmic metropolis, yet we are destined to explore only our own small local streets. This grand cosmic ocean, filled with 2 trillion islands, is also a gallery of stunningly diverse architecture. Galaxies are not all the same. They come in distinct shapes and sizes, a variety so consistent that astronomers have created a classification system for them, often visualized as a simple tuning fork. At one prong of the fork are the majestic spiral galaxies, like our own Milky Way and its neighbor Andromeda. These are the pinwheels of the cosmos, characterized by their flat, rotating disks and magnificent, sweeping arms that spiral out from a bright central bulge. These arms are actually density waves, cosmic traffic jams where gas and dust are compressed, triggering the brilliant birth of new, hot blue stars. This is why the spiral arms appear so bright and defined. Our solar system resides in one of these outer arms of the Milky Way, giving us a front row seat to this slow, celestial dance. On the opposite prong of the tuning fork sit the elliptical galaxies. These are the ancient giants of the universe, looking nothing like their spiral cousins. They are smooth, featureless, and often shaped like a football or a sphere, glowing with a soft, reddish-yellow light. This color tells a story of their stellar population. Elliptical galaxies are dominated by older, cooler stars, with very little of the gas and dust needed to create new ones. They are cosmic retirement communities, vast and quiet, having long ago exhausted their star-forming fuel, often through violent mergers. And then there are the galaxies that defy this neat classification, the irregulars. These are the chaotic, unstructured galaxies, often smaller in size and lacking any defined shape. Many of these galaxies owe their messy appearance to gravitational interactions, their forms twisted and distorted by close encounters or collisions with other galaxies. They are the living proof that the universe is a dynamic and often violent place, where a single galactic meeting can erase billions of years of elegant structure in a cosmic instant. Buried deep within the heart of nearly every large galaxy, including our own Milky Way, lies a monstrous secret, a supermassive black hole. At the center of our galactic home, a relatively quiet beast known as Sagittarius, a star holds sway. Its mass is almost incomprehensible, weighing in at a staggering 4 million times that of our Sun, all crushed into a region of space smaller than our solar system. These cosmic anchors are not rare anomalies, they appear to be a fundamental part of a galaxy's anatomy. But how does something so dense, so hidden, exert such profound influence over its entire host? The answer lies in its silent, relentless gravity. Even when dormant, a supermassive black hole's gravitational reach helps shape the very structure of the galaxy around it, governing the orbits of billions of stars and controlling the flow of gas from the galactic hinterlands toward the core. This is a delicate balance, however. When a black hole actively feeds, drawing in vast amounts of gas and dust, the scene transforms from one of quiet control to one of unimaginable violence and brilliance. The material spiraling into the abyss does not go quietly. It forms a superheated, swirling disk of plasma, glowing with intense radiation across the entire electromagnetic spectrum. Friction and magnetic fields become so intense that they can funnel some of the infalling material into jets of energy and particles that shoot out from the poles at nearly the speed of light, stretching for thousands of light years into intergalactic space. In this active state, the galactic core can outshine every single star in the galaxy combined, becoming a beacon visible across the universe known as a quasar. These are not merely distant lights, they are the birth cries of galaxies, the furious teenage years of a cosmic giant. The energy blasting from a quasar is so immense that it can blow away the very gas clouds that form stars, effectively putting a hard stop on a galaxy's growth. So while a supermassive black hole can spark a firestorm of star formation through its gravitational influence, it can also, in its most voracious phase, sterilize its own galaxy, deciding its ultimate fate. This hidden heart is not just a resident, it is the architect, the master of ceremonies for the entire galactic show. This silent, stretching cosmos reveals a truth more profound than any collision. Galaxies are not just drifting, they are fleeing. In the 1920s, astronomer Edwin Hubble made a discovery that shattered our static view of the universe. By observing the faint light from distant galaxies, he noticed their light was stretched, shifting toward the red end of the spectrum. This redshift was a cosmic speedometer, and it showed that nearly all galaxies are racing away from us. The farther away a galaxy is, the faster it appears to be receding. This relationship, now known as Hubble's law, paints a startling picture of a universe that is fundamentally and uniformly expanding. But what is it exactly that is expanding? The galaxies themselves are not simply flying through space like shrapnel from an explosion. Instead, the very fabric of space itself is stretching, carrying the galaxies along with it. Imagine the universe as a loaf of raisin-bread dough rising in an oven. As the dough expands, every single raisin moves away from every other raisin. No raisin is the center, yet from the perspective of any one raisin, all the others are moving away. This is precisely what is happening to our cosmic raisin bread. The space between galaxy clusters is continuously growing, creating an ever-widening gulf. This single, elegant observation was the first crucial piece of evidence for the Big Bang theory, the idea that our entire universe began from an immensely hot, dense state and has been expanding and cooling ever since. The echo of that initial event is still pushing the cosmic horizon farther away with every passing moment. Even the grand spiral we call home is not quite the perfect disk we once imagined. The Milky Way, it turns out, is warped. Recent, precise measurements of the positions of thousands of distant stars have revealed that our galaxy is profoundly bent, its outer disk twisting into a distinct S-shape, much like a vinyl record left too long in the sun. This is not a small imperfection. The warp is so extreme that stars tens of thousands of light years from the center are displaced upward or downward by thousands of light years, creating a colossal cosmic ripple. So what immense force could possibly bend an entire galaxy, a structure of hundreds of billions of stars held together by gravity? The primary suspect is a relentless gravitational tug of war. Our galaxy is not alone. It is orbited by dozens of smaller satellite galaxies, most notably the Large and Small Magellanic Clouds. As these smaller galaxies swing around the Milky Way, their combined gravity pulls on the dark matter halo that envelops us. This invisible scaffold, in turn, drags the entire galactic disk, forcing it into this slow, persistent wobble. But there may be an even more dramatic cause echoing from the deep past. This vast warp could very well be the lingering scar of a past collision, the ghost of a smaller galaxy that was torn apart and consumed by the Milky Way billions of years ago. Its final gravitational shudder is still rippling through our galaxy, a permanent deformation in the fabric of our cosmic home. The silent, sleeping giants of the cosmos reveal a profound truth about a galaxy's life cycle. While our Milky Way is a vibrant stellar nursery, many galaxies have reached the end of their creative road. These are the so-called dead galaxies, most often the vast elliptical spheres that glow with a dim, reddish hue. That color is the key to their story. Unlike the brilliant blue newborns that illuminate spiral arms, these galaxies are filled almost exclusively with ancient, aging stars billions of years old. They are cosmic retirement communities on a galactic scale, where the frenetic energy of star birth has ceased entirely. The reason for this stellar silence is a simple lack of fuel. All the cold gas and dust, the raw material for building new stars, has been either completely used up in a frenzy of past formation or violently stripped away. This often happens within the crowded environment of a galaxy cluster, where a galaxy plunging through the superheated intergalactic gas has its own star-forming fuel ripped from its grasp, as if caught in a powerful cosmic headwind. These red and dead galaxies are not just resting, they are fossilized, their final stellar populations destined to slowly cool and fade over trillions of years, becoming permanent monuments to a more energetic and creative past. The same gravitational chaos that forges new galaxies can also tear individual stars from their homes. During the slow-motion dance of a galactic collision, stars are not merely rearranged, some are violently evicted. As two galaxies intertwine, their complex gravitational fields act like a colossal slingshot. A star swinging too close to the galactic core can be whipped away with such immense force that it achieves escape velocity, hurled out into the blackness of intergalactic space. These become orphan stars, cosmic castaways on a one-way journey into nothingness. They are forever separated from the light and community of any galaxy, doomed to travel through the immense, cold voids between galactic clusters. Imagine our own sun, alone in that profound darkness. The night sky would be almost perfectly black, with no Milky Way band to grace the heavens, just the occasional, faint, fuzzy smudge of a distant galaxy. These stellar orphans are not rare. Astronomers estimate that trillions of such stars are adrift in the space around our own local group, a ghostly population of suns illuminating nothing but their own solitude. Their existence is a permanent testament to the violence of the cosmic mergers that shape the universe, a reminder that creation and destruction are two sides of the same celestial coin. These stellar orphans are a haunting reminder of the immense, empty spaces that separate the great gatherings of matter. Yet even the vast voids between galaxy clusters are not truly empty, for they are bordered by structures of such colossal scale they defy human comprehension. The largest single structure we have ever identified is not a supercluster itself, but a titanic filament of galaxies known as the Hercules Corona Borealis Great Wall. This cosmic behemoth is a web-like concentration of galaxies spanning an almost unimaginable 10 billion light-years from one end to the other. To put that into perspective, the entire observable universe is only about 93 billion light-years across. This single structure occupies more than a tenth of the known cosmos. It is not a solid wall, of course, but a gravitationally bound river of galaxy clusters, a dense thread woven into the grand cosmic web that makes our own local group feel vanishingly small. The existence of such an immense formation presents a profound challenge to one of astronomy's foundational ideas, the cosmological principle. This principle states that when you view the universe on a sufficiently large scale, it should look roughly the same everywhere, with matter distributed evenly in all directions. There should be no central point, no unique location, and certainly no structures so large they break the model of cosmic uniformity. The Hercules Corona Borealis Great Wall is so gigantic that it seems to violate this rule. It raises a startling question. Is this wall a statistical fluke, a rare overdensity in an otherwise uniform cosmos? Or is it a sign that our understanding of the universe's largest scales is fundamentally incomplete? The very rules we use to define reality itself are being tested by the shadow of this galactic leviathan. This galactic dance is governed by a rhythm that defies all common sense. If you were to watch a spiral galaxy like our own Milky Way spin, you would expect its stars to follow the same rules as our solar system. The planets closer to the Sun orbit at blistering speeds, while the outer worlds like Neptune move in a slow, stately crawl. Yet when astronomers measured the orbital speeds of stars in distant galaxies, they found something that shattered this expectation. Stars in the galaxy's outer arms, far from the bright central bulge, were racing around the center just as fast as the stars closer in. This is the galaxy rotation problem, a cosmic paradox that should not exist. According to the laws of gravity and the amount of visible matter we can see, those distant stars should be flung off into the void, their speed far too great for the galaxy's gravitational pull to hold them. The only logical explanation is that there is much more mass there than we can account for. This missing mass does not shine, it does not glow, it reveals itself only through its immense gravitational grip. This was the moment the ghost in the machine revealed its hand, providing one of the strongest and most direct proofs for the existence of dark matter. An invisible, massive halo must be enveloping the entire galaxy, its gravity holding the speeding outer stars firmly in their tracks. The beautiful spiral we see is just a luminous decoration pinned to a hidden, monstrous scaffold of matter we cannot see. This galactic hunger is a fundamental force shaping the universe. The largest galaxies grow not by creating new stars alone, but by devouring their smaller neighbors in an act of cosmic predation known as galactic cannibalism. Our own Milky Way is no peaceful giant, it is a predator with a clear and active appetite. Right now, it is in the process of digesting the Sagittarius dwarf spheroidal galaxy, a tiny companion that has been orbiting us for billions of years. With each pass, the Milky Way's immense gravity pulls this smaller galaxy apart, stretching it into long, shimmering streams of stars that wrap around our galactic core like celestial spaghetti. These are tidal streams, the ghostly remains of a galaxy being systematically dismembered. Astronomers are now mapping these faint stellar rivers in exquisite detail, and they reveal a violent history far beyond this single meal. These streams are like fossilized records of past encounters, showing us that the Milky Way has consumed dozens of smaller galaxies over its long life, growing fat on these cosmic snacks to become the grand spiral we call home. This ongoing feast is a stark reminder that the serene beauty of a galaxy often masks a brutal reality of survival and growth in the cosmic deep. Even the invisible spaces between the stars are not truly empty, but threaded with an unseen force. Woven throughout the vast expanse of a galaxy is a complex and sprawling magnetic field. These fields are unimaginably large, stretching for tens of thousands of light years across the entire galactic disk, yet their pull is astonishingly weak, millions of times weaker than a common refrigerator magnet. Do not let that frailty fool you, for these invisible lines of force are cosmic puppet masters, guiding the very stuff of creation. When a massive cloud of gas and dust begins to collapse under its own gravity to form new stars, the magnetic field within that cloud resists the collapse. It acts as a support structure, slowing the process down and preventing the cloud from fragmenting too quickly. This magnetic resistance is a critical regulator, ensuring that stars form at a measured pace and influencing whether a star is born as a solitary sun or as part of a vast, glittering cluster. Without this subtle, guiding hand, the stellar baby boom within a galaxy would be a chaotic and inefficient firestorm. These fields also serve as the universe's ultimate particle accelerators. Charged particles, known as cosmic rays, are hurled across the galaxy at nearly the speed of light. As these ultra-high energy particles travel, the galactic magnetic field bends their paths, twisting their trajectories into a random, tangled web. This makes it impossible for us to trace a cosmic ray back to its source, as its origin point is lost in a maze of magnetic curves. The field contains these raging particles, preventing them from simply flying off into intergalactic space, and in doing so, it shapes the very energy environment of the galaxy. You can think of these magnetic fields as the galaxy's subtle skeletal framework, an invisible architecture that guides its growth, contains its fury, and quietly orchestrates the birth of new suns from the chaos. The subtle magnetic fields that guide a galaxy's growth are ancient, but the very first galaxies to form in the universe appeared with shocking speed. The James Webb Space Telescope has peered back to the cosmic dawn, to a time when the universe was a mere few 100 million years old, and found a sky already glittering with mature galaxies. These are not just infant clumps of stars, but fully formed massive structures that should not, according to our best models, have had enough time to assemble. The prevailing theory suggested a slow, gradual process where tiny clouds of gas slowly coalesced over billions of years. Instead, we see a universe that hit the ground running, building colossal galactic cities in what amounts to a cosmic blink of an eye. This discovery turns our timeline of cosmic evolution on its head. It suggests the early universe was far more efficient and dynamic at constructing order from chaos than anyone predicted. Perhaps vast reservoirs of dark matter provided a ready-made gravitational scaffold for gas to rush in and ignite stars at a ferocious rate. Or maybe the first stars were born in a fundamentally different way, collapsing directly from immense, pristine gas clouds into behemoths we can no longer see. These ancient galaxies are a profound puzzle, their very existence challenging us to rewrite the story of how everything began. These brilliant blue blobs defy the quiet aging of so many galaxies. Scattered across the cosmos are rare, peculiar islands known as blue compact dwarf galaxies. They are small, isolated, and burning with a ferocious, youthful energy. Their entire being is consumed by an intense, galaxy-wide firestorm of star formation. This furious activity floods them with the light of countless newborn, massive, hot stars, which glow with an unmistakable, brilliant blue hue. They are cosmic cauldrons boiling over with creative fury. What makes these blue blobs so extraordinary is not just their color, but their profound simplicity. They are relatively pristine, containing very few heavy elements, the cosmic metals forged in the hearts of earlier stellar generations. This lack of complexity makes them invaluable living fossils. By studying them, astronomers are essentially looking through a window in time back to the early universe. In that ancient era, before many stars had lived and died, most galaxies would have looked like this, small and metal poor, erupting in frantic, brilliant bursts of starbirth. These modern-day blue blobs are not just oddities, they are relics, offering us a direct glimpse into the chaotic and fertile conditions of the cosmic dawn, when the universe was a far more vibrant and explosive nursery. Some galaxies do not have a single, stable heart, but instead pulse with multiple brilliant cores. This startling phenomenon is a direct and violent consequence of galactic cannibalism. When two large spiral galaxies collide and begin their slow merger, their central supermassive black holes are dragged into the chaotic dance. As the galaxy's structures are torn apart, their bright central regions, or nuclei, can temporarily coexist before finally merging into one. This creates a celestial beast with two beating hearts, a clear and visible sign of a recent catastrophic union. But the universe can produce an even more extreme spectacle. Look at the galaxy known as NGC 7674, a system that appears to have not two, but four distinct nuclei blazing at its center. This is not a single galaxy with four black holes from four separate mergers, but a complex cosmic train wreck. The prevailing theory suggests that this many-hearted monster is the result of a multiple galaxy collision. a rare event where several galaxies have plunged into one another in a relatively short span of cosmic time. The gravitational turmoil of such an event funnels immense amounts of gas toward the various cores, igniting them into a frenzy of star formation and black hole activity, making each nucleus shine with an intense, brilliant light. This multi-core state is a fleeting one, a cosmic snapshot of a temporary and violent phase. Over hundreds of millions of years, the same relentless gravity that brought them together will force these nuclei to spiral inward, eventually coalescing into a single, even more massive black hole, leaving the galaxy with one quiet, dominant heart. These multiple nuclei are the universe's way of showing us that the most dramatic transformations are often caught in the act, a fleeting moment of cosmic chaos frozen in time. The most massive structures in the cosmos might be the ones we cannot see at all. Littered throughout the universe are theoretical behemoths known as dark galaxies. These are not merely dim collections of ancient stars, but entire galactic-scale structures composed almost entirely of dark matter, with so few stars that they are effectively invisible to our telescopes. Imagine a ghostly, perfect copy of the Milky Way, possessing the same immense gravitational pull from its dark matter halo, but with only a handful of scattered stars to betray its existence. This is the haunting nature of a dark galaxy. So how do we hunt for something that emits no light? Astronomers have developed ingenious, indirect methods to find these cosmic phantoms. One technique involves scanning the skies for clouds of neutral hydrogen gas that are rotating far too quickly for their own good. If a cloud of gas is spinning at the speed expected for a full-fledged galaxy, yet contains almost no stars, it becomes a prime candidate for a dark galaxy. The only explanation for its rapid, stable rotation is the gravitational grip of a massive, unseen dark matter halo holding it all together. Another method relies on the universe's own magnifying glass, a phenomenon called gravitational lensing. When a massive object like a galaxy cluster lies between us and a distant, bright light source, its gravity bends and distorts that light, creating multiple, warped images or bright arcs. By studying these intricate cosmic mirages, astronomers can map the distribution of mass in the foreground cluster. Sometimes they find a concentrated lump of invisible mass that is bending the light, a lump with no visible stars to account for it. This gravitational signature points directly to the presence of a dark galaxy, its immense but unseen bulk warping the fabric of space-time itself. Finding these shadowy giants is crucial, as they could be the universe's most basic building blocks, the pristine dark matter halos predicted to form first before most of the stars ever had a chance to ignite. The very atoms that make up our world were born from the life and death of stars, a process that finds its grandest stage within the swirling arms of galaxies. Every element in the universe heavier than hydrogen and helium, including the iron in your blood, the calcium in your bones, and the oxygen you breathe, was forged in the heart of a star. This cosmic alchemy, known as nucleosynthesis, begins in the cores of stars where immense pressure and heat fuse simple hydrogen atoms into helium, releasing the energy that makes stars shine. In the final, dramatic stages of a star's life, whether in the searing explosion of a supernova or the violent collision of neutron stars, even heavier elements are created and then blasted outward at nearly the speed of light. This stellar material, rich with newly minted elements, is ejected into the vast spaces between the stars, the interstellar medium. Over billions of years, generation after generation of stars live, die, and seed this galactic reservoir with their chemical remains. A galaxy, therefore, is far more than a collection of stars. It is a giant recycling plant, a cosmic factory that slowly enriches itself. The gas and dust that will one day collapse to form new stars, planets, and even life is already sprinkled with the remnants of its long-dead ancestors. Our own solar system formed from a cloud that had been enriched by countless such stellar explosions. We are not just living in a galaxy, We are literally made from its processed, recycled, and ancient star stuff. This cosmic recycling of star stuff takes place on a timescale almost too vast for the human mind to grasp, a rhythm measured not in years but in galactic orbits. Our solar system is not stationary within the Milky Way. It is a passenger on a grand, circular journey around the galactic core. A single complete circuit, one cosmic lap around our home galaxy, defines a galactic year. This is not a quick trip. From our vantage point here on Earth, one galactic year lasts approximately 225 to 250 million of our own years. To truly feel the weight of that number, consider the entire history of complex life on our planet. The last of the dinosaurs were wiped out by an asteroid impact around 66 million years ago. In the immense timescale of our galaxy, that entire epoch, from the extinction event to the rise of humanity and all of recorded history, represents only about 1/4 of a single galactic orbit. All of human civilization, with its empires and inventions, its art and its wars, has occurred in less than a blink of a galactic eye. We are living through an infinitesimally small moment in our sun's long journey around its true cosmic home. Galaxies can be extinguished. Across the cosmos, brilliant stellar nurseries can fall permanently silent in a process astronomers call quenching, where a galaxy's ability to form new stars is violently and decisively shut down. This is not a gentle fading, but an active, often brutal, termination of a galaxy's creative future. One of the most dramatic quenching mechanisms occurs within the crowded environments of galaxy clusters. As a spiral galaxy plunges at millions of miles per hour through the superheated, thin gas that fills the space between cluster galaxies, it experiences an immense cosmic headwind. This is ram pressure stripping. Imagine driving a car at high speed through a torrential downpour where the rain seems to come at you horizontally, blasting the windshield. Now replace the car with an entire galaxy and the rain with a hurricane of million-degree plasma. The force of this impact is so powerful that it can literally blow a galaxy's precious reservoir of cold gas and dust straight out of its grasp. This gas is the very raw material for new stars. Once it is stripped away, the galaxy is left starved. Its remaining stars will age and redden, but no new blue suns will be born to replace them. The galaxy's spiral arms, once bright with young stars, will gradually dim and lose their definition, transforming the vibrant system into a red and dead relic. But starvation can also come from within. In many massive galaxies, the central supermassive black hole acts as a powerful regulator. When it feeds voraciously, the resulting active galactic nucleus or quasar unleashes unimaginable energy. Blasts of radiation and colossal jets of particles erupt from the core, flooding the galaxy with turbulent heat. This phenomenon, known as AGN feedback, does not just blow out a few gas clouds. It heats the entire galactic reservoir of star-forming fuel to such extreme temperatures that the gas can no longer collapse under its own gravity to form stars. It is as if someone turned up the thermostat in a nursery so high that no infant could possibly survive. The galaxy's own heart becomes its executioner, using its immense power to sterilize its home and quench the fires of creation. A galaxy that was once a thriving metropolis of stellar birth is forced into a permanent and often premature retirement. The record for the most distant known galaxy belongs to an object called HD1, a speck of light whose journey to our telescopes began a staggering 13.5 billion years ago. We are not just looking across space when we observe it, we are peering back through time to an era when the universe was a mere 300 million years old, a cosmic newborn. The light we detect today left HD1 long before our own planet, our Sun, or even the Milky Way galaxy had fully formed. This makes every photon a priceless relic, a direct messenger from the dawn of creation. By analyzing its faint signal, astronomers can decode the conditions of the primordial universe. They found that HD1 is impossibly bright, shining with a ferocious intensity that suggests it was either birthing stars at a frantic, unprecedented rate, a hyper-nursery creating hundreds of new suns every single year, or it was already powered by a voracious supermassive black hole, a cosmic paradox that should not have had enough time to grow so immense. Either scenario forces us to rewrite our models of how the first structures emerged from the darkness. Galaxies like HD1 are not just distant points of light, they are fundamental boundary tests for our understanding of physics itself, showing us a universe that was capable of building giants in the blink of an eye. Surrounding every galaxy is a colossal, seething atmosphere of gas so hot it defies our everyday experience. This is the galactic halo, a vast corona of multimillion-degree plasma that can stretch for hundreds of thousands of light years, completely enveloping the entire visible galaxy. If our eyes could see in X-ray light, the serene spiral of the Milky Way would appear as the brilliant core of a faint, ghostly sphere of unimaginable heat. This halo is not a minor feature, it is the single largest reservoir of normal matter a galaxy possesses. All the stars, planets, and glowing nebulae you see in a galactic portrait combined contain less material than this invisible, scorching shroud. Yet its incredible temperature is precisely what keeps it hidden from our optical telescopes and makes it so difficult to study. Gas this hot does not glow with visible light, it radiates intensely in high-energy X-rays. To even begin to map these halos, astronomers must rely on space-based observatories like the Chandra X-ray Observatory, instruments designed to see this specific, furious energy. So why does this matter? These halos are the galaxy's ultimate strategic reserve. They hold the potential fuel for future star formation, a vast ocean of raw material. But there is a catch. For that gas to collapse and form new stars, it must cool down and condense. Right now, it is so energetic that it simply cannot coalesce, like trying to build a snowman with steam. The great, unanswered question is what keeps these halos so intensely hot, preventing this cosmic fuel from flowing in and sparking a new era of stellar birth. The answer may lie in the explosive feedback from the galaxy's own supermassive black hole, whose periodic outbursts might be pumping energy back into the halo, effectively keeping the gas on a permanent boil and regulating the galaxy's growth from within its own invisible embrace. The galactic halos of superheated gas are not the only invisible giants hiding in plain sight. There exists an entire class of galaxies so faint they are nearly transparent, cosmic phantoms that challenge our most basic assumptions about galactic structure. These are the ultra-diffuse galaxies, or UDG. Imagine a ghostly imprint of the Milky Way, a sprawling disk stretching an impressive 100,000 light-years from end to end, but one that holds only a single % of our galaxy's stars. The result is a celestial entity of almost unbelievable sparseness, a ghost ship adrift in the cosmic ocean. Its stars are so widely spaced that if you were standing on a planet inside one, the night sky would be a profound and nearly perfect black, punctuated by just a few lonely, distant suns. The most famous of these, Dragonfly 44, was discovered hiding within the Coma Galaxy cluster. It possesses the full mass of the Milky Way, but almost all of that weight is locked away in an immense, invisible halo of dark matter. This presents a profound and puzzling contradiction. How can a galaxy be so massive, yet so utterly incapable of making stars? One theory suggests these are failed galaxies, systems whose dark matter halos formed perfectly, but which, for some unknown reason, never managed to pull in enough gas to fuel significant star formation. A more dramatic possibility is that they were once normal galaxies, but were stripped nearly bare by gravitational tides or that immense cosmic headwind ram pressure as they moved through their cluster, leaving behind only their most tightly bound stars and their dark, massive skeletons. Their existence forces us to ask a deeper question. What is a galaxy if not its stars? These ghostly forms tell us that the invisible dark matter scaffold is the true, durable essence of a galaxy, while the shining stars we see are merely a fleeting and sometimes absent decoration. Even the color of a galaxy can tell a dramatic story of cosmic upheaval. Astronomers searching through vast digital sky surveys stumbled upon a collection of tiny, bizarre objects that defied all expectations. They were small, compact, and most strikingly, they were a vivid, almost luminous green. These celestial objects were promptly nicknamed green pea galaxies. Their unusual hue has nothing to do with green stars, which do not exist in nature. Instead, that brilliant emerald color comes from an element essential for life, oxygen. Within these small galaxies, a firestorm of star formation is raging so intensely that it floods the surrounding gas with an unimaginable amount of ultraviolet radiation. This intense energy causes the oxygen atoms to glow with a specific, powerful green light, a phenomenon known as emission. Think of it like a colossal interstellar neon sign, where the gas is the tube and the furious birth of new stars is the electric current that makes it shine. These green peas are cosmic powerhouses, packing the star-forming punch of a galaxy 10 times their size into a tiny, chaotic package. They are not just a colorful oddity, they are a living window. Their frantic activity and simple chemical composition, low in heavy elements, mirror the conditions of the early universe when the first galaxies were assembling themselves in a frenzy of creation. Studying a green pea galaxy in our own cosmic backyard is like finding a tiny, vibrant time capsule, offering us a direct and tangible glimpse into the explosive teenage years of galaxy formation that occurred billions of years ago. Our own Milky Way is not a perfect, symmetrical spiral. It belongs to a special subclass known as a barred spiral, defined by a thick, elongated bar of densely packed stars that cuts directly through its galactic center. This central bar is not a small feature. It is a colossal structure spanning thousands of light years, with the entire spiral arm system emerging from its opposing ends. This central bar fundamentally changes the dynamics of our galactic home. It acts as a powerful cosmic traffic controller, its immense gravitational field orchestrating the flow of stars and gas. As stars orbit the galactic center, those that enter the bar's influence are pulled into new, radial paths, funneled inward along the bar's length before being slung out the other side into the spiral arms. This creates a vast circulating pattern, a slow but constant migration of stellar material. The bar's most critical role, however, involves the galaxy's fuel. It efficiently channels immense clouds of hydrogen gas from the outer disk toward the crowded galactic core. This inward rush of gas can trigger intense bursts of star formation in the central regions, and more dramatically, provides a steady food supply for the supermassive black hole, Sagittarius, a star lurking at the very heart of the bar. This single structural feature, a bridge of stars we cannot see with the naked eye, is a master regulator governing everything from stellar orbits to the feeding habits of the galaxy's hidden monster. The orderly structure of a spiral galaxy can be completely upended by a celestial anomaly, the polar ring galaxy. These are not merely warped disks, but systems where a brilliant ring of stars, gas, and dust orbits directly over the galaxy's poles, spinning at a perfect right angle to the main galactic plane. It is as if a colossal, luminous hula hoop has been thrown around a cosmic waste, creating a structure of stunning and impossible geometry. This perpendicular ring is not a minor feature. It can be larger than the central galaxy itself, a separate disk of matter caught in a dizzying, crosswise dance. The formation of such a spectacle requires a specific and violent cosmic event. The prevailing theory is a very precise galactic capture. A smaller, gas-rich companion galaxy ventures too close to a larger elliptical or lenticular galaxy. As it is torn apart by tidal forces, its material is not scattered randomly. Instead, the gravitational dynamics are just right to funnel the stolen gas and stars into a stable orbit that wraps around the poles of the larger galaxy. Over millions of years, this captured debris settles into a coherent, rotating ring, a permanent trophy from a past act of cosmic consumption. Another possibility is that the ring forms from the slow, steady accretion of intergalactic gas clouds, drawn in from the vast voids and funneled into this peculiar polar orbit by the larger galaxy's gravitational field. However they form, these rings are cosmic gyroscopes, their stable, perpendicular spin locking in the memory of a long-ago encounter. They are fleeting structures in galactic terms, lasting only a few billion years before the ring destabilizes and eventually merges with the main galaxy. To see one is to witness a temporary, beautiful, and violent imbalance in the cosmos, a rare snapshot of a galaxy caught in the act of digesting a meal in the most spectacular way possible. Even the death of a star can leave a ghostly imprint on its galaxy. When a supernova explodes, its flash of light does not simply vanish into the void. That initial, catastrophic pulse of radiation races outward at the speed of light, but it can encounter vast, dormant clouds of cosmic dust drifting through interstellar space. As the light slams into these clouds, it is reflected back toward us, but with a crucial delay. We see the initial flash, and then, years or even decades later, we see the reflected light finally arrive from these more distant dust sheets. The result is an expanding shell of light, a luminous echo that appears to pulse outward from the long-vanished explosion. One of the most stunning examples of this played out in our own cosmic backyard. After supernova 1987 erupted in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, astronomers watched in awe as not one, but multiple rings of light slowly materialized around the blast site. These were not new explosions, they were ancient dust clouds positioned at different distances from the supernova, being sequentially lit up like a chain of celestial lanterns. Each ring was a perfect circle, a fossilized snapshot of the original flash, revealing the intricate architecture of invisible dust lanes we never knew were there. A light echo is more than just a beautiful afterimage, it is a form of cosmic archaeology. By studying how these rings brighten and fade, astronomers can precisely map the distribution of dust throughout a galaxy, material that would otherwise remain completely hidden. It is as if the universe itself provided a flashbulb, illuminating the dark corners of a galaxy long after the photographer has left the room. Our own galaxy actively blocks our view of the cosmos. As we peer out from within the disk of the Milky Way, our sightline is completely obscured in one crucial direction, directly along the plane of our own spiral arms. This creates a great celestial blind spot astronomers call the zone of avoidance. It is a broad, dusty band arching across the sky where the familiar pinpoints of distant galaxies seem to vanish, hidden behind an almost solid wall of interstellar gas and cosmic dust. This isn't a small patch of emptiness, it obscures a full 20% of the entire universe beyond our own galaxy. For centuries, this zone represented a fundamental limit to our cosmic maps, a frustrating blank space in our charts of the large-scale structure of the universe. We knew the great cosmic web must continue on the other side, but we were effectively trapped inside, unable to see out. The solution was to stop trying to see with ordinary light. Visible light, the kind our eyes and optical telescopes use, is easily scattered and absorbed by all that intervening dust, like a car's headlights vanishing in a thick fog. To penetrate this cosmic veil, astronomers had to turn to other forms of light, ones that can slice straight through the obscuring material. Radio waves and infrared radiation pass through these clouds with ease. By using powerful radio telescopes to map the hydrogen gas in distant galaxies and infrared observatories to see the heat glow of their stars, we have finally begun to lift the veil. The discoveries have been stunning. Entire galaxies and even massive clusters of galaxies have been found lurking in that once empty zone. These are not small, faint systems, but major structures that were completely invisible to us just a few decades ago. Mapping these hidden giants has finally revealed the full, connected architecture of our local universe, showing that the filaments of the cosmic web continue seamlessly behind the brilliant but blinding disk of our own galactic home. The same cosmic violence that destroys galaxies can also give birth to new ones. When two immense galaxies tear into each other, their gravitational pull does not just rip stars from their orbits, it stretches vast rivers of gas and dust into long, luminous bridges between them. These are tidal tails, cosmic scars millions of light years long. Within these colossal streams, something miraculous can happen. The very same forces that pulled the gas out can cause it to become unstable. Dense knots of hydrogen and cosmic dust begin to collapse under their own gravity, igniting firestorms of new star formation. These are not mere star clusters, they are entire new galaxies in their own right, born from the wreckage of their parents. Astronomers call them tidal dwarf galaxies. They are the orphans of a celestial catastrophe, small and irregular in shape, glowing with the brilliant blue light of their youthful stellar populations. What makes these dwarf galaxies truly unique is their composition, or rather, what they seem to be missing. A normal galaxy, as we have seen, is dominated by an immense, invisible halo of dark matter that dictates its structure and holds it together. But a tidal dwarf galaxy forms from the visible, baryonic matter that was stripped away during the collision, the gas and dust that once resided in the galactic disks. The dark matter halo, being more diffuse and spread out, was largely left behind. This means these newborn galaxies may be made almost entirely of normal matter. This creates a fascinating cosmic paradox. Without the gravitational anchor of dark matter, how do these small galaxies hold themselves together against the centrifugal forces trying to tear them apart? The answer may lie in their own self-gravity. The sheer mass of all the newly formed stars and the remaining gas provides enough gravitational glue to bind the galaxy, at least for a time. Finding and studying these rare, dark matter, poor galaxies is like finding a natural laboratory. They allow us to test the laws of gravity and the nature of dark matter in a completely new context, observing how a galaxy behaves when it is built from the luminous stuff we understand, free from the overwhelming influence of the ghostly matter that normally rules the cosmos. Some galaxies burn so brightly they outshine entire universes of stars, yet their light is almost entirely hidden from our eyes. These are the hyperluminous infrared galaxies, cosmic powerhouses that radiate the overwhelming majority of their immense energy in the form of invisible, heat-like infrared light. To understand why they shun the visible spectrum, you have to picture the scene within one. These are not serene spirals, they are chaotic, dust-choked maelstroms, often the direct result of two galaxies colliding and merging into one. The violent union funnels colossal amounts of gas and dust toward the center, igniting a firestorm of star formation on an almost unimaginable scale. Hundreds, even thousands of new stars can ignite every single year compared to the Milky Way's sedate pace of just one or two. These newborn stars are massive, hot, and brilliant, but they are born inside thick, opaque cocoons of cosmic dust. The dust absorbs their fierce, visible light, heats up until it glows, and then re-radiates all that captured energy as a torrent of infrared radiation. It is like seeing a city shrouded in an impenetrable fog. You cannot see the individual streetlights or buildings, but you can feel the immense heat radiating from the entire blanket of mist. In some cases, the galactic merger also forces gas directly into the central supermassive black hole, awakening it into a ferocious quasar. This monster then adds its own unbelievable energy to the mix, further heating the dust to incredible temperatures. The galaxy becomes a pressure cooker where the combined fury of a stellar baby boom and a voracious black hole is trapped, transformed, and then released in a single, invisible, infrared blaze that can outshine a trillion suns. Our own galaxy has a long-lost sibling, a tragic story written in starlight. The Andromeda Galaxy, our nearest giant neighbor and future collision partner, was not always the majestic spiral we see today. It is a galactic cannibal, and its most famous meal was a massive galaxy astronomers have nicknamed M32P. This lost sibling was likely a large, respectable spiral in its own right, perhaps 1/3 the mass of the Milky Way, making it a true sibling in the cosmic family. Billions of years ago, it ventured too close to Andromeda and was utterly torn to pieces. The evidence for this ancient crime is not found by looking at Andromeda's bright disk, but by studying its faint outer halo. When a large galaxy is cannibalized, its stars are not instantly absorbed. They are ripped away and scattered into a vast, tenuous cloud that surrounds the predator galaxy, a ghostly shell of galactic remains. Using powerful telescopes and sophisticated computer models, astronomers have mapped this halo around Andromeda. They discovered that it is not a smooth, uniform cloud, but is instead littered with distinct streams and clumps of stars, all moving in similar, peculiar orbits. These are the stellar corpses of M32P, the shredded remains still coherent enough to tell their story. It is as if a detective found a family's scattered heirlooms all across a city, and by tracing their locations could reconstruct the exact path of a vanished ancestor. The final, chilling clue is the strange galaxy we now call M32. This small, compact elliptical galaxy orbits Andromeda incredibly closely, like a frantic moth around a flame. Astronomers now believe this dense little object is the surviving core of M32P, the galactic heart that somehow endured the catastrophic dismemberment of its body. It is the lone survivor of a cosmic massacre, a silent witness to the violent feast that allowed Andromeda to grow into the giant it is today. This discovery reshapes our own local history. The Milky Way was not the only grand spiral in the neighborhood. We once had a sibling, a rival, another major galaxy that shared our cosmic corner. That galaxy is gone, its stars and identity forever assimilated into the glowing bulk of our future destroyer, a permanent reminder that even among giants, there is always a larger predator. The violent death of a star is not an end, but a beginning that can reshape its entire galaxy. When a massive star explodes as a supernova, it does more than just scatter newly forged elements into space. The blast unleashes a colossal shockwave that slams into the surrounding interstellar medium, heating the gas to millions of degrees and blasting it outward. Combine this with the powerful stellar winds from countless other young, massive stars, and you create a force capable of lifting immense volumes of hot gas high above the serene plane of the galactic disk. This rising plume of superheated material forms a galactic fountain. Picture it not as a single stream, but as a vast, churning cycle. The hot gas surges upward for thousands of light years into the galactic halo, where it gradually radiates away its heat and energy. As it cools, this metal-enriched gas condenses into dense clouds that become so heavy they can no longer be supported by the surrounding pressure. They then begin to fall back down, plunging toward the disk like a cosmic rainstorm. This returning deluge of cooled gas provides the perfect, dense fuel for the next generation of star formation, effectively recycling the galaxy's own material in a continuous loop of creation. This is the galaxy regulating its own growth, a self-sustaining ecosystem on a truly cosmic scale. But sometimes the stellar violence is too extreme for this balanced cycle. In regions of intense starbirth, known as starburst galaxies, the combined fury of thousands of supernova and stellar winds can overwhelm the galaxy's gravity. Instead of a graceful fountain that recycles its water, the galaxy experiences a hurricane. The rising gas is heated with such ferocity that it never cools enough to fall back. It is instead launched outward at tremendous speeds, becoming a powerful galactic wind that blows straight through the halo and escapes the galaxy's gravitational grip entirely. This is a catastrophic loss for the galaxy. These outflows can eject the very gas that is the lifeblood of future stars, carrying it off into the vast intergalactic voids. In this way, the most vigorous episodes of star birth can actually sterilize a galaxy, quenching its ability to create new suns and hastening its transition into a red and dead relic. The same forces that build a galaxy can, in their most furious expression, tear it down from within. Even the blackness between the galaxies holds a faint, persistent light. A soft infrared glow permeates the entirety of space, a cosmic background hum that is the sum of all the starlight ever produced. This is the cosmic infrared background, and a significant portion of it is a direct gift from the galaxies themselves. Think of it as the combined murmur of a vast, invisible crowd. Our most powerful telescopes can pick out the brightest, most obvious voices in that crowd, the brilliant spirals and ellipticals that dominate our deep field images. But for every one of those, there are countless fainter galaxies, distant dwarfs, and shrouded starbursts whose individual light is too dim for our instruments to register. Their contribution does not simply vanish. Instead, it blends together into this universal, diffuse radiance, a collective whisper that fills the cosmos. This faint glow is therefore more than just a scientific curiosity. It is a fossilized record of the universe's total star formation history. By measuring its precise intensity and spectrum, astronomers can tally up all the starlight ever created, from the first brilliant blue suns at the cosmic dawn to the steady burn of modern galaxies like our own. It is the ultimate census of cosmic creation, proving that even the faintest and most forgotten galaxies have left their permanent mark on the fabric of the universe. This discovery of galaxies seemingly devoid of dark matter sent shockwaves through the world of astronomy. For decades, the existence of this invisible substance was the cornerstone of our understanding, the hidden hand that held every galaxy together. Then astronomers found NGC 1052 DF2, a ghostly, ultra-diffuse galaxy that simply did not obey the rules. When they measured the motions of its star clusters, they found them moving at a surprisingly slow, sedate pace. According to the laws of physics and the amount of visible mass present, this galaxy should be flying apart, its stars scattering into the void. The only explanation was that there was no extra mass, no dark matter halo providing gravitational glue. It was a galaxy built from the stuff we can see, and it was defying a fundamental cosmic law. How could such a thing exist? One compelling theory points directly to the violence of galactic collisions. NGC 1052 DF2 might be a tidal dwarf galaxy, one of those rare systems born from the gas and stars ripped free during a galactic merger. As we learned, these orphans form from the visible baryonic matter that was stripped away, while the more diffuse dark matter halo of the parent galaxies was left behind. This would create a galaxy naturally poor in dark matter, a celestial entity built from a different blueprint. Another, more brutal possibility is that this galaxy was once normal but had its dark matter violently ripped away. If it passed too close to the immense gravitational field of a much larger galaxy, tidal forces could have pulled the invisible halo apart, stealing the dark matter while leaving the visible stars relatively intact. This would be like having the invisible skeleton of a creature torn out, while its flesh and blood remained eerily in place. The existence of these anomalous galaxies does not disprove dark matter, but it profoundly refines its role. It suggests that while dark matter is the primary architect that draws gas together to form galaxies in the first place, the luminous, star-filled structures we see can, under very specific and violent circumstances, exist independently of their dark foundations. These missing dark matter galaxies are not errors in the cosmos. They are crucial exceptions that test the rule, forcing us to understand the universe not as a place of simple uniformity, but as a dynamic arena where many different creation stories are possible. This subtle alignment reveals a hidden choreography stretching across the cosmos. Galaxies are not spinning at random. Their rotations are often synchronized with the largest structures in existence, the cosmic web. When a galaxy forms deep inside one of those vast, river-like filaments of dark matter, its initial conditions are set by the flow. Think of the cosmic web not as a static sculpture, but as a colossal system of highways for gas and dark matter, all streaming steadily along these gravitational riverbeds. As this primordial material flows, it begins to spin, and that spin becomes the rotation for the newborn galaxy taking shape within the filament. This imprints a lasting direction, a kind of cosmic DNA that dictates the axis around which the galaxy will spin for billions of years. The result is that the rotations of neighboring galaxies, all forming within the same immense filament, can show a distinct alignment like countless leaves caught in the same gentle cosmic current. This phenomenon is not visible to the naked eye. It requires statistical analysis of thousands of galaxies to detect the subtle pattern. But its existence is profound proof that a galaxy's identity, even its very spin, is shaped by the architecture of the universe on the grandest possible scale, a permanent reminder of its humble origins within the flowing rivers of the cosmic web. This cosmic choreography can bend the very fabric of reality to create mirages. When we look deep into space, we sometimes see galaxies stretched into impossible shapes, long luminous arcs and perfect rings of light known as Einstein rings. These are not actual structures but celestial phantoms, the distorted images of galaxies that lie billions of light years behind a massive cosmic lens. This phenomenon is called gravitational lensing. The immense gravity of a foreground object, like a massive galaxy cluster, acts like a lens in space, warping the space-time around it. When light from a far more distant galaxy travels toward us, its path is bent as it passes through this warped region. From our perspective, that distant galaxy's light is magnified, smeared, and duplicated into multiple images, arcs, or a complete circle. It is as if the universe itself has provided a telescope of unimaginable power. This natural telescope allows us to see galaxies that would otherwise be far too faint and distant for any human-built instrument to detect. We are not just seeing a distorted picture, we are seeing a truth magnified. By studying the precise shape of these cosmic mirages, astronomers can map the distribution of all the mass in the foreground cluster, including the vast, invisible halos of dark matter that would otherwise remain completely hidden. The lens reveals the lens itself. This chance alignment in the sky is a gift, offering us a direct line of sight to the earliest epochs of the universe and providing a powerful tool to weigh the unseen skeleton that holds the cosmos together. The very atoms that forge new stars are not spread evenly across a galaxy. Journey inward from the galactic rim toward the bustling core, and you will find a silent but profound change in the chemistry of the cosmos. The abundance of heavy elements, what astronomers call metallicity, steadily increases the closer you get to the center. This is the galaxy's metallicity gradient, a permanent chemical record of its life story. The reason for this elemental gradient lies in the relentless cycle of stellar life and death. A galaxy's core is an ancient, densely packed metropolis where stars have been forming, living, and dying for billions of years longer than in the quieter outer suburbs. Each generation of massive stars ends its life in a supernova explosion, a cosmic forge that hammers hydrogen and helium into heavier elements like carbon, oxygen, and iron, and then blasts them back into the surrounding gas. In the crowded center, this process has repeated countless times, with each new generation of stars forming from gas that is already enriched with the metallic ashes of its predecessors. The result is an inner region that is chemically mature, its gas thick with the building blocks of planets and even life itself. In contrast, the galactic outskirts are like a frontier territory. Star formation has been slower and more sparse, with far fewer generations of stars to pollute the pristine gas. The raw material out here is still closer to its original, primordial state, dominated by the simple elements of hydrogen and helium that formed in the Big Bang. This chemical map tells a clear story of a galaxy growing from the inside out, its central heart having lived a far more intense and productive life, forever marking its territory with a richer, more complex atomic signature. This final stage of galactic cannibalism leaves behind a cosmic ghost town. Fossil galaxy groups are the serene, almost silent, in points of evolution within a galactic community. Imagine a group of galaxies much like our own local group, but one that has been left to its own devices for billions of years longer. In that immense span of time, a relentless process of gravitational attraction and merging has played out to its ultimate conclusion. All of the large, substantial galaxies have been drawn together, colliding and coalescing into a single, dominant giant elliptical galaxy that sits at the very heart of the group. This central galaxy is a behemoth, a cosmic monarch that has consumed all its major rivals. What remains is a system of profound inequality, a solitary giant surrounded by a faint, diffuse swarm of tiny, untouched dwarf galaxies. These small galaxies were never substantial enough to be drawn into the central merger. They are the silent witnesses orbiting at a safe distance from the ancient feast. This entire structure is then encased within a massive, hot halo of X-ray emitting gas, the last remnant of the violent, fiery mergers that built the central giant. A fossil group is not an active site of creation or destruction, but a relic. It is a snapshot of a process that has run its full course, a final, quiet state that reveals the ultimate fate of galactic neighborhoods that are left to evolve in isolation. By studying these cosmic fossils, astronomers can peer into the far future of our own local group, seeing the day when the Milky Way and Andromeda have long since finished their dance, leaving behind a single, colossal elliptical galaxy reigning over a court of silent, tiny dwarfs. The serene beauty of a spiral galaxy can be a brilliant lie, for some galaxies are not just collections of stars but colossal cosmic radio stations, broadcasting their power across the universe on a frequency our eyes cannot see. These are the radio galaxies, a distinct and dramatic class where the central supermassive black hole is not just active but screaming. The defining feature of these giants is a pair of colossal jets, unimaginable fountains of superheated plasma that erupt from the poles of the black hole and shoot outward at nearly the speed of light. These are not gentle outflows, they are the most powerful particle accelerators in the known universe, stretching for millions of light years, often far beyond the visible boundaries of the host galaxy itself. If our eyes could see in radio waves, the sky would be filled with these ghostly, titanic structures, each one a pair of opposing spears stabbing into the intergalactic darkness. The energy required to create and sustain these jets is almost beyond comprehension, generated by the violent, magnetic chaos of the black hole's accretion disk. As matter spirals into the abyss, intense magnetic fields can funnel some of that infalling material away from the poles, focusing it into tightly collimated beams that blast their way clear of the galaxy. This is active galactic nucleus feedback in its most extreme form. These jets do not just travel, they interact violently with their environment. When they plow into the tenuous gas that exists between galaxies, they deposit immense energy, heating the surrounding material and preventing it from ever cooling to form new stars. In this way, a radio galaxy can effectively sterilize its own future, using its most powerful engine to quench the very star formation that might have sustained it. The galaxy becomes a victim of its own heart's furious, invisible rage. Our own galactic backyard holds a puzzle that defies simple expectations. The dozens of small satellite galaxies orbiting the Milky Way do not swarm around us in a random, spherical cloud. Instead, they are arranged with an eerie precision, orbiting within a remarkably thin, flat plane that slices directly across the poles of our own galactic disk. Astronomers call this the vast polar structure, a great sheet of cosmic companions all moving in a coordinated dance. This is deeply strange. Our best supercomputer simulations of how galaxies form, based on the standard model of cosmology and dark matter, predict something entirely different. They show that the tiny leftover fragments of galaxy formation, these satellite galaxies, should be scattered in a roughly spherical halo, arriving from all directions over billions of years. The existence of this vast structured plane is like finding all the moons of Jupiter lined up in a single, perfect ring, a configuration that simply should not happen by chance. So what could force these independent galaxies into such a narrow, organized disk? One compelling idea is that they did not arrive individually but as a group. A whole flock of small galaxies may have fallen into the Milky Way's gravitational grasp together in the relatively recent past, and their shared initial trajectory has locked them into this common polar orbit ever since. Another, more radical possibility is that this structure is a permanent feature, sustained by a complex and still unknown interaction with the dark matter halo that envelops us. The vast polar structure is more than just a celestial alignment. It is a direct challenge, a cosmic clue that our understanding of the invisible scaffolding of the universe may still be missing a crucial piece. Even the most carefully planned observations of the cosmos are subject to a kind of celestial prank. Galaxies can photobomb each other in the vastness of space, creating a happy accident that reveals secrets invisible to a direct gaze. This cosmic alignment occurs when a foreground galaxy drifts directly into our line of sight to a much more distant background galaxy. From our vantage point, the closer galaxy acts like a natural screen, its silhouette blocking the brilliant light from the galaxy far behind it. This is not a simple eclipse, it is a diagnostic tool. Astronomers can analyze the subtle ways the background galaxy's light filters through the foreground galaxy. By measuring precisely which wavelengths of light are dimmed, they can map the distribution of cosmic dust within the photobombing galaxy. Dust, which is otherwise incredibly difficult to see directly against the blackness of space, reveals itself by preferentially absorbing blue light. The result is a detailed, natural blueprint of the foreground galaxy's dusty skeleton, its spiral arms and dark lanes traced out in shadow against the brilliant backdrop. This chance alignment, a fleeting cosmic coincidence, gives us a free and incredibly detailed laboratory to study the raw materials of star formation in a galaxy we were not even trying to observe. But this cosmic journey from vibrant blue to quiet red is not always a sudden leap. Between the brilliant, star-forming spirals and the ancient, red and dead ellipticals lies a mysterious middle ground astronomers call the Green Valley. This is not a place you can point a telescope toward, but a critical transition zone on a special chart that plots galaxy color against galaxy brightness. Galaxies in the Green Valley are caught in a cosmic act of metamorphosis. They are the galaxies that were recently part of the blue cloud, alive with the light of young, hot stars, but are now in the process of shutting down. Their star formation is slowing to a crawl, and their color is shifting as their brilliant blue stars die out, leaving behind the longer-lasting, cooler, redder stars to dominate the galactic light. That subtle shift toward a greener hue on the chart is the telltale sign of a galaxy crossing a fundamental threshold, moving from a vibrant, creative youth toward a quiet, settled retirement. Studying these Green Valley galaxies is like finding a patient in the middle of a mysterious illness, giving us our best chance to diagnose what is actually killing star formation across the cosmos. Is it the slow, inevitable starvation of a galaxy simply using up its last reserves of cold gas? Or is it a more violent, active quenching event where a supermassive black hole erupts and blows away the star-forming fuel, or where a galaxy plunges through a cluster and has its gas stripped by that immense cosmic headwind? By looking at galaxies in this critical transitional phase, we can see which of these processes are actively at work, their signatures fresh and not yet faded by billions of years of silence. The Green Valley is the universe's most important crime scene, holding all the evidence we need to solve the mystery of galactic death. Deep within the cosmic hum of a galaxy, a steady, silent pulse keeps time. This rhythm does not come from stars or gas, but from the celestial clocks known as pulsars. These are the ultra-dense, rapidly spinning cores of long-dead massive stars, beaming out radiation with a precision that rivals our best atomic clocks. Astronomers are now learning to listen to an entire galaxy's worth of these pulses simultaneously, and in their subtle collective ticking, they are hearing a new kind of music. The rhythm of these pulsars is not always perfectly steady. Their incredibly regular beats are sometimes minutely disrupted, arriving at our telescopes a fraction of a second early or late. These are not random errors. Imagine a quiet pond, its surface dotted with floating corks. If you were to drop a massive stone into the center of that pond, a ripple would spread outward, gently lifting and lowering each cork in a predictable sequence. The pulsars are our corks scattered across the galaxy. The ripples disturbing their perfect timing are gravitational waves, not from small events, but from the most colossal dances imaginable. The disruptions are thought to be caused by the slow, inward spiral of pairs of supermassive black holes, each billions of times the mass of our Sun, orbiting one another in the hearts of distant, merged galaxies. As these monstrous binaries circle each other, they churn the very fabric of space-time, sending out these faint, low-frequency ripples that wash through our entire galaxy. No single pulsar can prove their existence, but by monitoring an array of them, a galactic network, scientists can see the correlated shifts, the signature of the wave passing by. This creates a gravitational wave background, a permanent, low symphony of spacetime vibrations left over from eons of galactic collisions. We are just beginning to sense this cosmic heartbeat, a deep and resonant thrum that is the echo of every giant black hole embrace that has ever shaped the universe. Our galaxy is a layered structure, a cosmic record of its own violent history. The familiar band of the Milky Way is not a single, flat disk, but is actually composed of two distinct stellar components, one nested within the other. Our own Sun resides in what astronomers call the thin disk. This is the galaxy's vibrant modern district, a relatively narrow plane where most of the gas and dust is concentrated. It is here that star formation continues today, illuminated by the brilliant, short-lived blue stars that define the spiral arms. But enveloping this thin disk is a much more ancient and diffuse structure, the thick disk. This component puffs out thousands of light-years above and below the galactic plane, a vast halo of older, redder stars that moves in more chaotic, tilted orbits. This thick disk is our galaxy's fossil record, a relic population of stars that formed in the Milky Way's chaotic youth. The most compelling theory for its existence points to a dramatic, ancient merger. Billions of years ago, a smaller galaxy likely plunged into the primordial Milky Way. The gravitational shockwaves from that collision would have violently stirred up the early disk, scattering stars into these puffed-up orbits and funneling gas inward to create the new, thinner disk we see today. Every time we look up at the band of the Milky Way, we are seeing more than just stars. We are witnessing the permanent scar of a long-ago catastrophe, the ghost of a collision that shaped our home into the layered city of stars it is today. Some galaxies are so choked with cosmic dust that their true nature is completely hidden from our view. These are the submillimeter galaxies, cosmic powerhouses engaged in a star-forming frenzy of almost unimaginable intensity. While our own Milky Way calmly produces one or two new stars each year, these distant giants are birthing hundreds, even thousands of suns annually, a stellar baby boom that would dwarf our entire galactic neighborhood. Yet if you were to look at one with an ordinary optical telescope, you might see nothing more than a faint, indistinct smudge. The very process that makes them so brilliant is also their perfect disguise. All those newborn stars are massive, hot, and incredibly luminous, but they are swaddled at birth in thick, opaque cocoons of dust. This dust, the sooty ash from previous stellar generations, absorbs nearly all of their fierce, visible, and ultraviolet light. It does not simply vanish that energy, however. The dust particles heat up until they glow, radiating all that captured starlight back out into space, but they do so at a much longer, colder wavelength in the submillimeter part of the spectrum. This is a light our eyes cannot see, a faint, heat-like whisper that requires enormous, specialized radio telescopes high in the dry Chilean deserts to detect. When we finally train these instruments on these seemingly dim objects, the truth is revealed in a blaze of invisible glory. What appeared to be a quiet galaxy is suddenly one of the most luminous objects in the universe, shining not with the light of stars, but with the thermal glow of dust heated by a firestorm of creation raging within. These dusty star formers are often the result of colossal galactic mergers, where the collision of two gas-rich spirals funnels immense amounts of raw material into a central cauldron, igniting a brief, spectacular, and self-obscuring chapter of hyper-starbirth. They are a brilliant reminder that the universe's greatest acts of creation often happen behind the darkest of curtains. But even this grand motion is not entirely our own. Our entire local group is caught in a gentle, relentless current driven by the universe's emptiest places. We are being pushed by a void. To one side of our galactic neighborhood lies one of the largest known structures in the cosmos, the local void. This is not a place of darkness filled with faint, distant galaxies, but a region of profound, almost absolute nothingness. It stretches for hundreds of millions of light years, a cosmic desert so vast that entire superclusters of galaxies could fit inside its borders with room to spare. Within this void, the number of galaxies drops to nearly zero, creating a staggering deficit of matter. And in the strange balance of cosmic gravity, emptiness exerts its own kind of force. Think of the universe as a hillside where dense clusters of galaxies are the peaks and the voids are the deep valleys. Matter naturally wants to flow downhill from the dense regions toward the empty ones. The relative emptiness of the local void creates a gravitational slope. While we are powerfully pulled toward the immense concentrations of mass like the Great Attractor, we are simultaneously pushed from behind by the absence of mass in the void. This is because the expansion of the universe stretches these empty regions even faster, effectively enlarging the valley and giving us a slight but measurable shove. Our motion through the cosmos is a delicate dance between being pulled by the universe's greatest gatherings of matter and pushed by its most profound absences. We are not just sailing through space, we are surfing a wave created by the contrast between everything and nothing. These ancient star clusters are cosmic fossils, each one a dense, spherical swarm of up to 1 million stars. Unlike the scattered open clusters in a galaxy's disk, globular clusters are incredibly old, often over 12 billion years, making them nearly as ancient as the universe itself. They do not orbit within the galactic plane, but instead move in vast, looping paths high above and below it, tracing out the invisible dimensions of the galaxy's halo. The number of these clusters a galaxy possesses is a direct measure of its violent past. A massive galaxy like Andromeda boasts over 500, while our own Milky Way has about 150. Each one is a story of assimilation. When a large galaxy like ours consumes a smaller dwarf galaxy, the victim's globular clusters are not torn apart. Their stars are so tightly bound by gravity that they remain intact, becoming permanent trophies captured by the cannibal. The clusters themselves are the surviving witnesses to these ancient mergers, their orbits preserving the memory of their original galactic home. Their chemical makeup tells an even deeper story. Some clusters contain stars rich in heavy elements, suggesting they formed in the crowded, polluted environment of a large galaxy's core. Others are chemically pristine, made of the pure hydrogen and helium that filled the early universe. indicating they were the first stellar systems to form in tiny, long-vanished protogalaxies. By simply counting these clusters and reading their chemical signatures, astronomers can reconstruct a galactic family tree, tracing the lineage of mergers and acquisitions that built the majestic spiral we see today from the chaotic collisions of the distant past. Even the profound emptiness between galaxies is an illusion. That cosmic ocean is not a true void, but a delicate, sprawling web of primordial gas known as the intergalactic medium. This is the universe's ultimate reservoir of normal matter, the very stuff you, I, and all the stars are made of. Surprisingly, most of the atoms in the cosmos are not locked inside galaxies, but are adrift in this vast, invisible network. This tenuous gas is incredibly diffuse, often with just a single atom floating in a space the size of a typical closet. Yet, when you add it all up across the colossal expanse of the cosmic web, it accounts for far more material than all the stars and galaxies combined. This is the raw fuel of creation itself. Galaxies do not simply exist in isolation, they are constantly feeding. They act like giant sponges, slowly drawing this pristine hydrogen and helium from the intergalactic filaments that surround them. The gas follows the dark matter highways of the cosmic web, flowing into the gravitational wells of galaxies, where it can eventually cool, condense, and ignite into new generations of stars. Every galaxy, including our own Milky Way, is still growing today by siphoning this ancient material from the spaces between worlds. So when you gaze at the blackness between the stars, you are not looking at nothing. You are witnessing the source, the primal ocean from which all galactic islands first condensed, and the same reservoir that continues to shape their evolution even now. Our journey through these 50 cosmic truths brings us to a final, profound realization. Every fact, every distant galaxy, and every invisible force we have explored is not just an abstract concept out there. It is the story of our own home. We are inside a galaxy, our planet, our solar system, and every single person who has ever lived exists within the sprawling disk of the Milky Way. This is our fundamental address in the cosmos, not just a point on a map, but the very fabric of our celestial neighborhood. This unique position shapes everything we know about the universe. We are not external observers looking at a model from a distance. We are participants living deep within one of the universe's primary structures, trying to comprehend the whole from a single spinning room. Our view is both privileged and profoundly limited. We can study the detailed anatomy of our own galactic home, count its stars, and map its dusty spiral arms, but we can never see its full face in a single glance. To understand the true shape of the Milky Way, we had to piece it together like detectives solving a mystery from the inside, using the clues offered by other, more distant spirals. This inside perspective is the lens through which all of cosmology is filtered. Our understanding of dark matter, galactic collisions, and stellar life cycles is built upon the evidence we can gather from this one specific location. The entire cosmic web, with its 2 trillion galaxies, is a reality we have inferred while living on a tiny rock, orbiting a typical star, tucked away in a single arm of a single-barred spiral. This is the ultimate context for our existence. We are not just looking at the universe, we are a small, conscious part of one of its most magnificent creations, forever seeing the cosmos from within. From the ghostly grip of dark matter to the spectacular collisions that forge new worlds, this journey reveals a cosmos in constant, beautiful turmoil. We have seen that galaxies are not static islands, but dynamic beings born from chaos, shaped by invisible forces, and destined to merge and evolve in an endless cosmic dance. They are cannibals and creators, their brilliant spirals and quiet ellipses telling stories of furious birth and serene old age. The scale is almost beyond comprehension, with trillions of these stellar cities adrift in a web of unimaginable size, most of them forever beyond our reach. And yet, our understanding is not fixed in stone. Every new telescope, from the James Webb peering into the dawn of time to gravitational wave observatories listening to the hum of black holes, rewrites our cosmic story, revealing deeper layers of mystery. The universe is far stranger and more wonderful than we ever supposed, so the next time you find yourself under a clear night sky, look up, see the faint band of the Milky Way, our own galactic home, and remember the incredible truths it holds. You are not just looking at stars, you are gazing into a living, breathing, and violently creative universe. What fact from our journey changed your perspective the most? Share your favorite piece of galactic wonder in the comments below.